The year is 2003. The vision is ancient. Link the world's two largest continents. But the solution is audacious. A high-speed rail tunnel spanning 3,000 miles beneath the hostile, crushing darkness of the Atlantic Ocean. This was the dream of the transatlantic hypertunnel. The success of this project would have fundamentally redefined global travel, logistics, and resource distribution. It was an engineering blueprint that truly should have changed history. But the project failed not because of a lack of genius, but because the ocean presented three distinct, unanswerable physical and financial hurdles. The tectonic time bomb. The tunnel's route crosses the Mid-Atlantic Ridge, the single largest, most active geological fault line on Earth. This is where continents tear apart. Building a rigid tunnel here is not engineering, it is tempting fate. Engineers had to design massive, flexible joints that could absorb unpredictable, continuous tectonic shifts of several meters without imploding. The crushing abyss and the instant coffin. At its operating depth, the tunnel would withstand pressure capable of instantly crushing any conventional structure. A single microscopic manufacturing flaw in a weld, intensified by the constant kinetic stress, would trigger an instantaneous, non-recoverable implosion, destroying the tunnel segment and killing everyone inside in less than a single second. The tunnel was a continuous, 3,000-mile-long pressure vessel where perfection was the only safety margin. The unthinkable maintenance lie. The estimated cost soared into the multiple trillions of dollars. But here is the critical promise for modern engineers. Even if the tunnel were built for free, the annual maintenance costs for fighting corrosion and repairing microfractures in the abyss would bankrupt every nation involved. The project was deemed economically unmaintainable. The story of this abandoned hypertunnel is not merely history. It is a cautionary tale that defines the limits of modern civil engineering and explains why current projects like Hyperloop are forced to stay on land. We will reveal the specific, terrifying geological flaw they discovered beneath the ridge, a flaw that would have guaranteed the collapse of the tunnel before the first train ever ran. The biggest enemy was not water. It was the planet's internal motion. The Mid-Atlantic Ridge is the most active seismic zone imaginable for a civil project. It is the boundary where the North American and Eurasian plates are constantly separating. This geological spreading is slow, perhaps only centimeters per year, but it is continuous and cumulative. The sheer scale of the tunnel meant it had to accommodate miles of tunnels being perpetually pulled apart. The theoretical solution involved gigantic, ultra-strong, articulated seismic joints. Imagine segments of the tunnel resting on spherical bearings and hydraulic dampeners designed to allow movement in 3 axes, all while maintaining a perfect, high-pressure seal against the ocean. Designing a seal that could withstand tens of thousands of pounds per square inch of pressure while remaining flexible enough to absorb a sudden fault displacement was technologically impossible with contemporary materials. A rupture in one of these critical joints would not be a leak. It would be a catastrophic pressure failure. The inrushing water would create an enormous vacuum effect, potentially destroying dozens of adjacent segments through pressure oscillation. Furthermore, the ridge is marked by hydrothermal vents, visual cue, diagram of hydrothermal vents near the tunnel. Zones where superheated, mineral-rich water erupts from the seafloor. The heat and chemical corrosion from these vents would rapidly degrade even the most exotic titanium alloys used for the hull, accelerating corrosion and metal fatigue. The tunnel was not being built in static rock. It was being built on a dynamic, hot, growing, and constantly changing geological wound. We will show you the exact material science failure that proved the structure could not last even a single human generation, that counteract the enormous pressure and the hostile geochemistry of the deep ocean. The transatlantic tunnel required an unprecedented commitment to exotic materials science. The hull could not be standard steel or even conventional concrete. It required massive quantities of ultra-high-yield titanium and composite superalloys. The challenge was twofold: pressure resistance and corrosion endurance. Titanium offers superior strength-to-weight ratio and exceptional resistance to to saltwater corrosion. However, the sheer volume of titanium required for a 3,000-mile structure made the cost astronomical. More importantly, the use of titanium alloys introduced new, terrifying risks. When titanium is stressed under constant load in a cold, deep-sea environment, it becomes susceptible to stress corrosion cracking. This is a slow, insidious process where microfractures propagate through the material, often without any visible external warning. The relentless, constant pressure of the abyssal plane would exploit these invisible cracks, making them grow faster and deeper. The engineers calculated that even with the most advanced alloys, the mean time between failures, MTBF, for a single hull segment was unacceptable. Guaranteeing structural integrity across thousands of miles required a technological leap that had not yet occurred. The only theoretical solution involved continuous active monitoring and repair by robots, which leads us back to the crippling cost and logistical impossibility. The failure to achieve long-term material stability beneath the Atlantic explains exactly why modern submersibles and deep-sea drilling operations are still temporary. The deep ocean simply demands a level of material perfection that humanity cannot afford or reliably sustain for an indefinite period. The next great failure was logistics, revealing why any emergency would spell an irreversible disaster for the entire Eastern Hemisphere. Even setting aside the trillion-dollar construction cost, the operational logistics of the transatlantic tunnel were a guaranteed recipe for catastrophe. The tunnel was too long, too deep, and too remote for any viable emergency response. The tunnel's primary lifeblood would be its ventilation and air quality systems. A breakdown in the air scrubbers, a localized fire, or a pressure anomaly would create a life-or-death crisis for passengers trapped inside the rail cars. The distance from the surface ports of entry, often spanning hundreds of miles, meant that rescue teams and specialized equipment would require days, not hours, to reach the deep mid-Atlantic sections. The only way to service the mid-ocean sections was through massive, deep-sea maintenance chambers and pressurized safety habitats built into the tunnel structure every few hundred miles. These chambers would need to be colossal, capable of holding repair crews and emergency air supplies, all while withstanding the crushing external pressure. These habitats themselves represented additional, massive points of failure and maintenance expense. The simple physics of an emergency breach were insurmountable. A catastrophic implosion in one segment would instantly flood the adjacent segments. Sealing and dewatering even a mile of deep-sea tunnel would be a construction feat rivaling the original project itself, taking years and billions of dollars. The entire system lacked the fundamental redundancy required for safe public transport. The project was deemed a single, continuous point of failure. This led to the chilling final abandonment, where the project's fate was sealed by something faster and cheaper than any tunnel. The final, definitive abandonment of the transatlantic hypertunnel came not from a geological report, but from a strategic market analysis. By the time the technical feasibility reports were at their peak, two competing technologies had rendered the entire concept obsolete. First, supersonic and hypersonic air travel. The continued refinement of jet engine technology and the conceptualization of hypersonic flight meant that the promise of a faster-than-air journey was already being fulfilled by the aerospace industry. Why spend trillions on a static, high-risk tunnel when commercial aircraft could already deliver faster, point-to-point travel with minimal infrastructure liability? Second, global fiber optic networks. The rise of massive, high-capacity fiber optic cable networks running along the ocean floor completely eliminated the communication need for a physical tunnel. Information and global commerce could flow instantly and cheaply through the existing undersea infrastructure, proving the fixed tunnel was unnecessary for the knowledge economy. The transatlantic hypertunnel remains a magnificent symbol of utopian thinking, but it was defeated by the simple reality that flexibility, speed, and lower cost always win over brute force engineering. The trillions in estimated costs were deemed better spent on developing global air freight and digital infrastructure. The tunnel, which should have connected the world, was ultimately shelved because the world connected itself faster, cheaper, and safer without it. The legacy of this abandoned megaproject continues to haunt modern engineers. We will next reveal the specific, terrifying design flaw in the tunnel's ventilation system that would have turned the mid-ocean journey into a guaranteed, slow-motion disaster, a flaw that modern Hyperloop designers are still struggling to overcome. Faced with the impossible challenge of the Mid-Atlantic Ridge, engineers did not surrender. They proposed a radical, multi-layered solution for the critical tectonic zones, the armored segment. This was essentially a tunnel within a tunnel, designed to combat both crushing pressure and geological movement. The primary hull would be a massive, dual-chamber structure of high-yield steel and concrete. But the tectonic sections would be encased in a secondary, colossal, flexible sheath built from exotic materials, designed to act as a sacrificial buffer. This outer sheath would absorb the initial shock and shear forces from the moving tectonic plates, protecting the inner rigid rail tunnel. However, this solution introduced horrifying logistical problems. The space between the inner and outer hull would need to be continuously pressurized or filled with a specialized, non-corrosive, inert fluid to prevent collapse. Maintaining the integrity of this fluid layer across miles of actively moving rock and massive pressure differentials was technically impossible. A breach in the outer shield meant the inert fluid would escape, transferring the full tectonic stress directly to the primary rail tunnel, guaranteeing collapse. Furthermore, the construction of the armored segment would require the invention of a new class of deep-sea tunnel boring machines, TBMs, that were nuclear-powered, pressure-rated, and capable of operating autonomously for months without human intervention. The cost and liability of such specialized, deep-sea TBMs were deemed too extreme. The engineers designed the perfect solution to the tectonic problem, but in doing so, they only multiplied the number of catastrophic failure points. Beyond the structural fears, the transatlantic tunnel presented an unsettling, existential threat to the marine environment that was ultimately deemed an unacceptable geopolitical risk. The structure would run through thousands of miles of deep-sea ecosystems. The most critical environmental concern was acoustic pollution. The constant, low-frequency hum and vibration generated by high-speed trains or Hyperloop vehicles operating within the tunnel, combined with the continuous, loud operation of the ventilation and pumping stations, would transmit through the dense rock and water for hundreds of miles. This perpetual noise would create a massive zone of acoustic disturbance for deep-sea marine life, including whales and dolphins, who rely on silence for navigation and communication. There was also the risk of thermal pollution. The vast machinery required to maintain the inner environment, including air cooling and dehumidification, would constantly vent residual heat into the cold abyssal water. This thermal plume, though slight, could disturb the delicate balance of the deep ocean ecosystems, particularly near the hydrothermal vents. The geopolitical fear was a precedent. The successful construction of this permanent, trillion-dollar infrastructure would set a global precedent for nations to claim rights over the international seabed for massive construction projects, potentially triggering disputes over deep-sea mineral rights and marine research zones. The project was canceled because it was deemed an act of environmental aggression and an infringement on the legal sanctity of the international seabed. The rail tunnel concept proved too costly. Conceptual planners explored a new, futuristic alternative, adapting the tunnel for a Hyperloop system. The Hyperloop idea involves transporting vehicles in low-pressure vacuum tubes at near supersonic speeds. However, moving the Hyperloop concept from land to the deep ocean abyss introduced a chilling, self-defeating paradox. On land, the primary threat is atmospheric pressure. Under the ocean, the primary threat is hydrostatic pressure. The Hyperloop tunnel requires maintaining a near-perfect vacuum inside the structure to minimize air resistance. This means the tunnel hull must not only withstand the colossal external water pressure, but must also resist the internal pressure differential created by the vacuum. The deep ocean pressure would constantly try to collapse the tunnel inwards, while the internal vacuum would offer no opposing resistance. Any flaw, any microfracture, or any leak in the colossal hull would not merely introduce water. It would cause the outside pressure to instantly crush and shatter the vacuum tube, with the force of the deep sea filling the void. This made the pressure tolerance requirements for the Hyperloop tunnel exponentially higher than for a simple pressurized rail tunnel. The engineers realized the only way to make the Hyperloop safe underwater was to make the tunnel walls impossibly thick and dense, driving the material cost even higher and rendering the system financially absurd. The Hyperloop concept in the deep ocean was defeated by the very vacuum it required for speed. The logistical nightmare of the tunnel culminated in the terrifying risk assessment for an internal emergency, specifically fire. On land, a tunnel fire is manageable through vertical vents and external access. At the bottom of the Atlantic, a fire would be an unstoppable disaster. The tunnel's ventilation system, spanning thousands of miles, would be fragile and complex. In the event of an internal fire, the production of toxic smoke and the rapid consumption of oxygen would create a crisis measured in minutes for thousands of trapped passengers. The distance between emergency ventilation shafts would be immense, making natural air exchange impossible. The only solution was a highly complex, internal pressurized air delivery system with massive, decentralized oxygen reserves. Maintaining these reserves and the accompanying filtration systems across the entire length of the tunnel would require constant maintenance and incredible energy expenditure. Crucially, the heat from an internal fire would rapidly compromise the internal structure, potentially leading to thermal stress on the outer pressure hull. While the external water would cool the hull, the internal stresses caused by the heat differential could accelerate material fatigue, risking a slow, grinding failure of the pressure shell itself. The entire tunnel would be designed to withstand tectonic plates, but it would be fatally vulnerable to a simple electrical short circuit. The terror of a guaranteed, unrecoverable disaster ultimately solidified the military and financial decision to abandon the project. The legacy of the transatlantic hypertunnel is the final lesson in deep-sea engineering. The ocean grants no second chances. Every terrestrial or aerospace project allows for failure, recovery, and learning. A bridge can be repaired, a plane can be grounded, but the ocean abyss demands perfection. The massive external pressure means that a structural failure is not a leak. It is an instantaneous, violent implosion. There is no time for emergency protocols, no survival window, and no feasible recovery operation for the debris scattered under miles of water. The engineering feasibility studies concluded that the system was too complex to ever achieve the necessary zero-defect manufacturing and maintenance integrity required for human life support across its entire length. The project was not abandoned because it was technologically impossible to build a single segment. It was abandoned because it was statistically impossible to build and maintain thousands of segments over centuries without a catastrophic, permanent loss of life and capital. The failure to build this tunnel taught the world what the true limits of infrastructure are. Next, we will reveal the specific, terrifying design flaw in the tunnel's ventilation system that would have guaranteed a slow-motion disaster, a flaw that modern Hyperloop designers are still struggling to overcome, proving that the $3 trillion problem still exists. The final, terrifying flaw of the transatlantic tunnel was not structural, but atmospheric. This is the design problem that continues to haunt modern Hyperloop concepts and was the guaranteed, slow-motion disaster of the underwater tunnel. The tunnel required massive pumping stations to move air across its 3,000-mile length. But the movement of trains or Hyperloop vehicles creates a piston effect within the narrow tunnel. Every train entering the tube shoves an enormous volume of air before it, creating powerful pressure shockwaves that on land, this is managed through vertical ventilation shafts. But beneath the ocean, vertical shafts are impossible. This meant engineers had to design colossal, horizontal bypass tunnels to vent this air pressure, effectively requiring the construction of a second or third auxiliary tunnel running parallel to the main line. This instantly doubled or tripled the overall construction cost and complexity. But the real nightmare lay elsewhere. Every train pushing air also creates a massive pressure void behind it. This means passengers waiting at mid-tunnel stations or rescue workers operating in technical compartments would face sudden and extreme pressure differentials, potentially causing barotrauma, nosebleeds, or internal organ damage. The tunnel would be dangerous to passengers even when it was not leaking. Viewer, this specific problem is why Hyperloop must use a vacuum on land, because managing air pressure at depth proved impossible without guaranteed disaster. During the Cold War, massive infrastructure projects were always viewed through the lens of national security. Although the transatlantic hypertunnel concept was primarily civilian, the military leadership of both sides raised grave reservations. For the United States and NATO, a fixed tunnel connecting continents represented an unacceptable security risk. The tunnel would be one continuous, unmonitored route for potential sabotage or for the movement of hostile assets during a major conflict. While controlled, it is an asset. If compromised, it becomes a massive strategic vulnerability. The worst scenario involved the potential for weaponization. Theoretically, the tunnel could be used for the concealed placement of strategic ballistic missiles or for providing secure, submerged communications between military bases. This dual-use potential meant that any attack on the tunnel during wartime would be justified as a military necessity. From a military standpoint, a single fixed infrastructure asset was far too easy a target, particularly in the era of growing accuracy of intercontinental ballistic missiles, ICBMs, which could strike the tunnel's endpoints. The tunnel was too valuable in peace and too vulnerable in war. To understand the complete financial collapse of the transatlantic tunnel, we must look at a far smaller, yet successful precursor, the Channel Tunnel, or Eurotunnel, connecting France and Great Britain. The Eurotunnel is only 31 miles long and is positioned at a shallow depth, within geologically stable chalk bedrock. It deals with no tectonic plates and no extreme pressure. Its construction was one of the most expensive and complex projects in European history, plagued by massive budget overruns and delays. Now compare that scale. The transatlantic tunnel would be 100 times longer, 30 times deeper, and situated within the most seismically active geological zone on Earth. If the Eurotunnel faced financial catastrophe, the transatlantic tunnel was a guaranteed multi-trillion-dollar collapse. The construction difficulties faced by the Eurotunnel, such as unexpected water breakthroughs and ground shifts, would be microscopic compared to the problems encountered thousands of feet beneath the ocean. The budget analysis and technical problems experienced by the successful Eurotunnel, completed in the early 1990s, served as the final, sobering proof that the transatlantic hypertunnel was a financial fantasy. The geological and financial lessons learned from the small tunnel definitively buried the dream of the massive one. The transatlantic tunnel was abandoned, but its legacy is not one of complete failure. It served as the ultimate proof of concept for the limits of infrastructure. Its collapse informed engineering decisions across the board, setting the boundaries for what is considered practically achievable. Its key lesson: when distance and depth exceed a certain threshold, flexibility and dispersal always win over rigidity and concentration. That principle is why we now rely on thousands of miles of flexible, constantly replaced fiber optic cables and global air freight networks, rather than one massive, fixed, single point of failure tunnel. Today, we see its conceptual echoes in projects like Elon Musk's Hyperloop and the Boring Company. These companies seek to solve the same problem: fast, high-volume transport over long distances. But they learned the essential lesson from the transatlantic plans. They must stay on land, where maintenance is accessible, pressure is low, and the cost of repair is manageable. The transatlantic tunnel represents the boundary where engineering ambition met geological reality. It demonstrated that even with unlimited theoretical funding, some physical challenges on Earth, like the constant movement of tectonic plates and the crushing hydrostatic pressure of the abyss, are simply too immense, too volatile, and too costly to maintain for a project requiring centuries of operational life. The transatlantic hypertunnel remains a magnificent symbol of utopian ambition, a dream of linking the world by rail that was ultimately defeated by the unyielding forces of the deep. ocean and an impossible financial equation that we have explored the three terrifying reasons for its failure. The mid-Atlantic tectonic time bomb, the instant coffin pressure risk, and the crippling trillion-dollar maintenance lie. The ultimate truth is that the ocean demands perfection, and humanity cannot afford to maintain perfection over 3,000 miles for perpetuity. The final question remains. Given the current advancements in automation, high-strength carbon fiber composites, and autonomous TBMs, do you believe that a future generation will ever possess the technology and the political will to connect the continents beneath the abyss? Or has the ocean definitively won this engineering war forever? Let us know your thoughts on the future of transoceanic travel in the comments below. If you enjoyed this deep dive into the lost future of engineering, like this video and subscribe to the channel for more stories about the incredible projects that were never built.